M&M's Mars claims the proportion of blue peanut butter M&Ms in each bag is 20%. When we did our segmented bar graph back in chapter 3, we counted the different colors of M&Ms and found that proportion. We got 21 out of 155 blue M&Ms. So that is our sample. Does the content of that bag, this sample, contradict the company's claim that there are 20% blue M&Ms? So we are going to first start by writing our hypotheses. Our null hypothesis is that the company is telling the truth. What is their proportion that they claim? P equals 0.20, 20%. Our alternative, we're going to do a two-sided test for the practice, is that it's not equal to 20%. That it's either more or less. We don't know which direction, but we think they might be lying, so we're going to test it. Or we want to know if they're lying, so we're going to test it. Okay. My p hat here, 21 out of 155 is what? It's pretty low. 0.135. Okay. So we only got 13.5% blue M&Ms in our bag. They say there should be 20% in their bags. So then I'm going to do what? Check conditions. So is 155 less than 10% of all M&Ms?
Yes.
Yes. Notice I'm writing the whole sentence. Okay, I'm modeling the good behavior for you. You should be writing the whole sentence, not just writing 10%, check. 155 less than 10%, check. You need to say what is less than 10% of. Okay, so what is your population? And is the sample representative? I can guarantee you I was not in Stater Brothers labeling the bags of M&Ms from 1 to however many there were and getting my calculator out and randomly generating a number to pick the bag of M&Ms. Well, I already look like a weirdo checking out with 12 bags of M&Ms. So I choose not to even look even stranger by randomly selecting them, getting my marker out, numbering their, it's just not going to work that way. Okay? Maybe. Okay, wait till we get to the Oreo experiment. I check out with like 10 packages of Oreos. I'm like, it's for an experiment. It's for an experiment. They're not all for me. Okay, so it's not a random sample. I didn't do a random sample, but is it reasonable to believe that that sample is probably representative of the rest of the bags in the United States?
Yeah.
Probably, right? So when we don't know or can't say it's random, we can say if it's reasonable that it's representative, right? So we'll say the sample is representative. And then our NP and NQ, NP hat greater than or equal to 10, we had 21. Right? I don't need to multiply 0.135 times 0.155. I'm going to get 21 point something because I rounded. It's 21. 21 successes. That's how many blue M&Ms I got. If we only got 9 blue M&Ms, we would not be allowed to continue. Okay, because it's not greater than or equal to 10. And then 155, NQ hat. Actually, you know what? That is wrong. That is wrong. Because we are assuming that their hypothesis is true. We have to check 155 times 0.2. And 155 times 0.8. Because we want to know, based on their percentage that they claim, should there be at least 10 successes and failures. So we have to check that condition with the hypothesized value, not our sample. Okay? So 31 and 124 So we're good since conditions are met. A normal model is appropriate. I will use a one proportion z-test. I can abbreviate one prop z-test.
And the other one you use is the one prop z-interval?
Yes, the one you did on the quiz was the one proportion z-interval. Okay, and then next chapter we talk about error, what can go wrong. We talk about setting that level where we'll always use that number to decide to reject or fail to reject. And then the next chapter we do the two proportion z-test and z-intervals. Okay, so I'm going to calculate my standard deviation based on the hypothesis. 0.2 times 0.8 divided by 155. And then we're going to draw a model. I get 0.0321. My mean is the hypothesis, 0.2. It's not really in the middle. It's bugging me. So 0.232. Yes, P naught is a hypothesized probability. Yeah, let's like. Just so you have that in there. And 0.296. .168. 0.136. And 0.104. So there's our normal model. Okay. Now, this is a not equal to test, which is a two-tailed test. We're interested if it's off by that amount in both directions. So when we're looking at this, we're really looking at, here's our hypothesized value right there, 0.135, right? There's my p hat, there's my sample, right? Just barely 2 standard deviations from the mean. So we have that side. But we're also interested in if it's the same distance on the other side from the mean. Okay, so we're going to draw the just barely over 2 standard deviations from the mean on this side as well. So a not equal to is a two-tailed test. And we have both the just barely 2 standard deviations on the lower end. So we're going to calculate this with less than, and then we're going to multiply by 2 because it's symmetrical. And so this side should be exactly the same, even if my drawing's bad. Right? Say that again? No, because I don't want the in-between area. I want the lower boundary. And so then you're doing center and subtracting from, right? So we'll just do the normal CDF. So we're going to calculate our test statistic, okay? I'm going to throw out a little bit more vocabulary today. The test statistic is my z-score. That's all. It's called the test statistic, the z-score. How do I calculate z-score? My sample. What's my sample? .135, right? minus the hypothesis, 0.2, divided by the standard deviation we already calculated. Okay. And that gives us I got negative 2.025. Remember that you have to do the subtraction, hit enter, and then do the division. Right? And use your picture to help see if you have the right number here, right? This negative 2. We said it's just barely more than 2 standard deviations, right? So our numbers should reflect what our picture reflects. Okay, so that's just like kind of something you can use to help check to just make sure you did that calculation correctly. And then we find our p-value by doing normal CDF and multiplying it by 2. So we're going to do normal CDF, negative 99, negative 2.02. When it's a two-tailed test, the sign of the z-score will tell us whether I'm using negative 99 or positive 99. If it's negative, I want the lower part, negative 99, and then I'll times it by 2. If it's positive, I'm given the upper part, so I'm going to do positive 99 and then times it by 2. So whatever I get here, negative 99, negative 2.02, I get 0.0217, and I'm going to times it by 2 because it's not equal to two-tailed. .0434. That is my p-value. So we multiplied it by 2 because it's a not equal to test. I'm not just interested if it's less than what they say. I'm interested if it's less than or greater than. I don't care which direction. Then we can interpret our p-value. There is a 0.0434 chance of obtaining a sample as extreme or more extreme than 0.135 if the true proportion of blue peanut butter M&Ms is 20%. If the null hypothesis is true, this is the probability of getting our sample or something more extreme. Okay. Which means it's unlikely that it's just sampling variation. Maybe they've changed it since the last time I got this statistic from their website. So what is our conclusion? We are going to reject. So, since my p-value of 0.0434 is so low, remember that under 5% is definitely no low enough. Between 5 and 10% is kind of a judgment call. Okay, is so low, I reject the null hypothesis. There is enough evidence to convince me the true proportion of blue M&Ms, peanut butter M&Ms, is not 20%. Now, if we were to fail to reject, say it was like 13% was our p-value, we would say, since my p-value is so high, I failed to reject the null hypothesis. There's not enough evidence to convince me the true proportion of blue peanut butter M&Ms is not 20%. It's a double negative statement. Okay? It goes against everything your English teachers teach you, but statistics is not English. Okay? We can never say anything with certainty, so we have to have that double negative. There's not enough evidence to convince me it's not 20%, but I'm still not convinced that it is 20%, because another bag of M&Ms could come around and cause us to reject. Okay? So, when we reject, we create an interval, right? Now you want to know the calculator shortcut for the interval? How about I teach you that? Okay, so get those calculators out. If we're creating an interval after a hypothesis test, my conditions are already met. All I have to do is create the interval and say what I believe it is. Okay, so to create an interval, you're going to go into your stat over to tests. I have z-test. We're not using the z-test. Stat is right there next to your xt theta n button. I'm going to a 1 proportion z interval is what I need to create. I already did the test. Yes, there's a calculator command for the test. We need to get familiar with doing it by hand, and then we can start using shortcuts, okay? I'll teach you the shortcut for the test tomorrow, okay? I don't think you're going to do a full test by hand tomorrow. The t-test.
Oh, I thought you meant like an actual test. Wait.
Stat over to tests, and you're going to scroll all the way down to 1 prop z int. It's a. Okay?
But this is for last chapter, yeah?
Yes. How many successes did we have? X has to be a whole number. I had 21. You cannot put a decimal in for X. If you don't have like 21 out of 155, then you have to calculate what X is, but you have to round it to a whole number. The calculator is like error. You can't have half of a success. Okay, so X has to be a whole number.
Oh, C level.
I had 155. C level is the confidence level. And then I can hit calculate.
That's cool. Yeah, that's
Okay, and you are allowed to use this on the AP exam. You will be allowed to use this on the next quiz and test. Okay, because all that work, you still have to check the conditions. You still have to be able to interpret this interval. Okay, so I am 95% confident. The true proportion of blue peanut butter M&Ms is between 0.0816 and 0.189. And somewhere I have to actually write this down, not just have it in my calculator. So you write 0.08161, comma 0.18936, and the only thing you have to do to show work is write on top 1 prop z int. 1 prop z int.